Tests about a population mean, first of all, looking for the conditions of inference. If you have a population mean, most probably you are going to be using a t-distribution with n minus 1 degrees of freedom. There's just the rare case for the AP purposes. There's the rare case where the population standard deviation sigma is known, and in that case, then use a z. So you would use a z. But normally, and some textbooks even say over 30, they would use a z. But for the AP test, we're going to say that we're going to always use a t if we have sample standard deviation, and we will use a z only when we have known standard deviation based on previous studies or some other reason like that. So the finding the test statistic is generic. You're going to be using that sample value minus the population value, and then your choice of what to use down here. If known standard deviation, you'll be using sigma, but more likely you'll be using the standard error of the mean, and so you'll be using this right here. Okay, so then to find that. Now, how can we know when we're able to find probability? We need to have the normal condition met. And so when n is less than 15, in order to do that, we need to have data that is roughly symmetric. That would be no evident violation for the shape. It's hard to tell at that low level under 15 what the shape is, but just make sure that there's no real evidence for a violation in that symmetric shape. You definitely want no outliers. So that would be basically that. And then if you are between 15 and 30, you can have some slight skew evident, not very, very skewed, but just some slight skew is okay. But you would still need to have no outliers in order to use that. When you are over 30, equal to or over 30, then the central limit theorem is met. And so then in that case, you can find the probability. If you had outliers, you probably would run the test twice, once with the outliers and once without the outliers, if possible. And then, of course, if your data was already nearly normal to begin with, even at n equals 1, if they state that it's nearly normal data to begin with, then, of course, you can go right to finding probability. Where the company claims to have developed a new AAA battery, and supposedly it lasts longer than regular AAA batteries. Based on years of experience, the company feels that its regular batteries last for 30 hours of continuous use. So we're wondering if these new batteries last longer than that. The simple random sample of 15 new batteries lasts 33.9 hours with a standard deviation of 9.8 hours. That was a sample standard deviation. And we want to know, does this data give us convincing evidence that the new batteries last longer on average? So this is a situation of means where mu is going to be the average life of the AAA battery, batteries in hours. And right now, we think that 30 hours is what the old style batteries did. But we have the new batteries, and they come out with a sample mean of 33.9 hours with a sample standard deviation of 9.8 hours. And so we're going to see if we can run a one sample t-test for means to see if we have convincing evidence, which means statistical evidence, that these new batteries last longer. Because right now we can't tell if 33.9 is that different enough that this is making a difference. Okay, so start off by, are we doing something that's random? This was an SRS of batteries, so that's good. So we have something random. Like we wouldn't want to just take batteries all from, like one store. Maybe they were in a garbage pile or something. I don't know. Look for violations of randomness. None there. Okay, independent, because this is going to allow us to find that standard error. Do our calculations with standard deviation. So is it independent? Is 15, because we have a finite number of batteries, is 15 less than or equal to 10% of n? It does seem reasonable that there are over 150 batteries. So that means we have independence. And you probably, for this situation, could have maybe made the case that the life of any one battery doesn't affect the life of any other battery. That probably would have been an acceptable independence check for this situation. Okay, and then now the nearly normal. Now, they didn't say it was nearly normal in the problem, so we can't just say because it's already nearly normal, it's nearly normal. We have to look at the size. We're looking at an n equals 15. So, yeah, like we actually would need information about the shape, of the data, because even though this is robust, we need to know, because this is not meeting CLT. Now, if it was already nearly normal, we'd be okay, but since they don't have information about that, we would need to know. And we also would need to know if there were no outliers. So we cannot do the t-test for means because cannot establish normalcy. Okay, so going on to the next page. Oh, well, this is nice. We actually have some data here about our batteries. So now we're going to look at that and see if we have enough information to then meet the normal condition. So the first graph we're looking at is the dot plot. And the next one is a box plot. And the last one is a normal probability plot. And you would want to provide, if you're checking the conditions as the part of the AP test, you'd want to provide a rough sketch of these graphs, or they might give you the graphs and you have to discuss them. So in the dot plot, which, a histogram would work too. In this dot plot, what we're seeing is that there is no clear skew. So that's good because we're at the 15 level, so that's a very small data set. And we can see that it's maybe roughly symmetric. From the box plot, I can see that box plot or box and whisker plot, I can see that there are no outliers. And also that it does look roughly symmetrical there as well. So that reinforces that conclusion. And then my normal probability plot, which is usually the best probability plot, is usually your best bet at looking for violations. And since it is roughly straight, that's the evidence that we need to be able to conclude that the conditions for inference are met. Since t-tests are robust, and so that's basically, we can do a one sample t-test for means. So just to summarize, you're going to be checking those conditions. You need to establish that it is nearly normal. That's so that we're going to be able to find a probability. And as they say here in this statement, the probability distribution needs to be nearly normal. That is by inspecting the graphs or already. Those are two ways to establish that, or establishing it through CLT, which is n greater than or equal to 30. So that would be your second method of establishing it for means. And then, of course, as with any situation, you do need to have independence, and that is what's allowing us to do this, the standard error, in this case standard error, because we have a sample standard deviation. And then we're going to write the hypotheses. I'm going to do the example with the batteries on the next page. We're going to write the hypotheses, and we'll either have an upper tail, a lower tail, or if we have the two-tailed case, then don't forget that you need to double your p-value when you have the two of them. And the calculator commands that are going to help us do all this are inverse t, which looks like inverse normal, and t-CDF, which looks like normal CDF, but notice that they both take the degrees of freedom instead of the mean and standard deviation. And always verify your results of anything that you do, because it's so easy to do with the stat test t-test on the calculator. Make sure you're verifying that. So here's our battery case, and we know that the conditions met. We know that we are doing a one sample t-test for means. We know that mu is 30, x bar is 33.9, standard deviation 8.9. These are all hours. And that is with a sample size of 15. So, start off by writing your hypotheses. Population symbol, statement of equality, bring the value that was the population value down. Alternative hypothesis, same population symbol. We are just wondering if these batteries last longer, right? Longer, right here. So we are going to be doing this situation with the 30 in the middle. We only care about this tail here because that is better batteries. So greater than 30. We're looking at the 33.9. Now we're going to find our t-test statistic, not a z, a t, and that is mean, sample mean minus population mean over. And if you want to write out the standard error of the mean, you can do that if you want. if you want to write it off to the side, that is. Square root of 15, and so that gives us a value of 2.53034912. So I'll bring that over, 2.53034912. I've got a t-statistic of 1.5413. Now I can't use this t-statistic without knowing its degrees of freedom. So degrees of freedom, which is n minus 1, there are 15 minus 1, there's 14 degrees of freedom on this curve. So I put it into the calculator and I find the probability of a t being greater than a 1.5413, and I use TCDF. Let's see, I'm going to start with my 1.5413. I'm going to put a big number, and I'm going to put my degrees of freedom in there, and that will come out with my value that I write on my paper of 0.07277. Okay, what alpha were we testing this at? I don't think they said, so I will use an alpha equals 0.05 because that's my favorite one. Okay, since the p-value of 0.07277 is greater than alpha equal 0.05, we fail to reject the null hypothesis and there is not convincing evidence that the batteries last longer. That the batteries last longer. And since they said these are more expensive, these new batteries would be more expensive, I would say don't change production to the new style batteries. Okay, so that's basically the conclusion there. I don't think that they last longer. Oop, I should say here than 30 hours. That was a close one. Put that right in there. And so hopefully we've made the right decision, and that's the decision we're making. But if you wanted to think about what type of error may have occurred in this situation, the type of error that might have occurred would be that we, because we failed to reject, that would be the only other possibility would be type 2 error. We definitely didn't do type 1 error. So I just want to bring up the calculator so I can just check this just to show you how you would always check your answers. So stat tests, that's why it's so important to know what kind of test you're doing. We're not doing an interval, we're doing a test, and we are doing a t-test. They don't even say the one sample on it. We are going to do it with summary stats. You can also have your t-test run with data. My x-bar was 33.9. My standard deviation was, and you put in the original one that you got because now I'm putting in the sample size, so it's going to find the standard error for me. And then I am doing looking for only the upper tail test, so I'm going to do that. and I could calculate, and I could even hit draw if I wanted to see it, and you can see that it comes out with the same t-test and the same p-value that we just found. So make sure you always check your answers using the calculator.